So, here's something worth thinking about as you settle in tonight. Above the roof of whatever building you're lying in, past the ceiling and the insulation and the tiles, there is a sky full of light arriving from an enormous range of different moments in the past. The light from the moon left about a second and a third ago. Sunlight, if it's still that kind of hour where you are, took a little over 8 minutes to get here. The light from the nearest star beyond our own left more than 4 years ago, back when you were a noticeably different person, living a noticeably different life. And some of the faintest smudges visible through a decent backyard telescope are carrying light that started its journey before there was anything on this planet you would recognize as an animal. None of it arrives labeled. It all just looks like little white dots. And here's the part people tend to skip past. No human being has ever touched anything beyond the moon. Not a hand, not a probe, not a machine. 12 people walked on the lunar surface between 1969 and 1972, and that is the entire extent of physical human contact with anything that isn't Earth. Everything else, every single distance you have ever heard quoted about the cosmos, was worked out by inference, by geometry, by people standing on the ground with instruments, measuring angles, and thinking very carefully about triangles. So when someone tells you the observable universe is about 93 billion light-years across, the interesting question isn't whether that's a big number. Obviously, it's a big number. The interesting question is, how could anyone possibly know that? How do you measure a distance you can never cross, to an object you can never reach, using nothing but light that has already arrived? That's what we're going to work through tonight. Slowly, one step at a time, starting from the ground beneath the building and working outward. And at every step, we're going to look at how that particular distance was actually measured, and by whom, and how they knew they hadn't made a mistake. There's no rush at all. If you drift off somewhere between here and the Andromeda Galaxy, that's completely fine. The universe will still be exactly that size in the morning, and the story will still be here. Let's start where the story actually starts, which is not with telescopes or satellites or any of the equipment you'd expect. It starts with a stick standing upright in the sun. Around 240 BC, in the Egyptian city of Alexandria, there was a man named Eratosthenes. He ran the library, which, if you know anything about the ancient world, is roughly the most interesting job available at the time. The Library of Alexandria was the great scholarly institution of the Mediterranean, sitting near the harbor in a city founded by Alexander the Great less than a century earlier. And Eratosthenes was its chief librarian under the Ptolemies. He was, by every account we have, relentlessly curious about basically everything. He wrote on geography, poetry, mathematics, history, and music. His contemporaries apparently nicknamed him Beta, the second letter of the Greek alphabet, which was not entirely a compliment, the suggestion being that he was second best at a great many things rather than first at any one of them. That reputation has aged extraordinarily badly, because Eratosthenes did something nobody had managed before. He measured the Earth. Here's how, and it's genuinely one of the most satisfying pieces of reasoning in the history of science. He knew about a well in the town of Sienne, far to the south, up the Nile, where the modern city of Aswan sits today. And the well had an unusual property that local people had noticed and talked about. On one particular day of the year, around the summer solstice in late June, at noon, the sun sat directly overhead. Sunlight reached all the way down to the bottom of the well and lit up the water. A vertical column cast no shadow at all. Now, Eratosthenes was several hundred kilometers north of there, in Alexandria, and on that same day, at that same noon, he had a vertical rod planted in the ground, a gnomon, and that rod did cast a shadow. So think about what that actually means. If the Earth were flat and the sun's rays arrived parallel, then a vertical rod in Syene and a vertical rod in Alexandria would either both cast shadows or neither would. Why would one place get a shadow and the other place get nothing on the same day, at the same hour, under the same sun? There's only one comfortable answer. The ground is curving between them, and the angle of that shadow tells you how much. Eratosthenes measured it at about 7.2 degrees, which is a very tidy number, because 7.2 degrees is exactly 1/50th of a full circle of 360 degrees. So the arc of ground between Alexandria and Syene, whatever that distance turns out to be, represents 1/50th of the entire circumference of the planet. All he needed now was that one distance, and this is the part people usually don't know about. Ptolemaic Egypt employed professional distance walkers called bematists, whose actual job was to pace out routes with a deliberately regular stride and count their steps. These were trained specialists, and their measurements of routes across the empire were remarkably consistent. The bematists put Alexandria to Syene at roughly 5,000 stadia. So Eratosthenes multiplied. 5,000 stadia, 50 times over, gives 250,000 stadia for the whole circumference of the Earth. Converting that into modern units is slightly awkward, because we aren't completely certain which stadion he was using. Different regions used slightly different ones. Depending on which you pick, his answer lands somewhere between about 39,000 and 46,000 kilometers. The real figure, the equatorial circumference of the Earth, is 40,075 kilometers. So somewhere in that range, a librarian in Egypt, working with sunlight and a rod and the counted footsteps of professional walkers, got the size of the entire planet right to within a few percent. More than 2,200 years ago, without leaving the Mediterranean, without a telescope, without any instrument more sophisticated than a stick planted in the ground. And the number, honestly, is the less interesting part. What matters is the method. Eratosthenes needed only two assumptions to make it work: that the Earth is a sphere, and that the sun is far enough away that its rays arrive essentially parallel. Given those two things, geometry does the rest. And geometry doesn't care in the slightest whether you can reach the thing you're measuring. That's the template. That's the entire ladder, right there in miniature. Every rung we climb tonight uses the same basic trick. Find something you can measure. Find a geometric relationship between that thing and the thing you actually want, and let the mathematics carry you across a gap your body could never cross. From here, the distances stop being walkable, and the first place we have to go is straight up. The moon is the only thing out there that anyone has ever actually gone to, and it's worth sitting with how odd that is. Everything beyond it, every planet and star and galaxy in this entire story, has only ever been looked at from a distance. So how far away is it? The first person to seriously attack that question was a Greek astronomer named Aristarchus from the island of Samos, working around 270 BC, roughly a generation before Eratosthenes. And Aristarchus had an idea that was, in principle, completely correct, and in practice completely defeated by the equipment available to him. Here's the idea. When the moon is exactly half lit, when you see that perfect straight line down the middle, the sun and the moon and the Earth have to be sitting at a right angle. The right angle is at the moon. Sunlight is hitting it side on. That's geometry, and it can't be otherwise. So if you know one angle in a right-angled triangle, you know the shape of the whole triangle. And the angle Aristarchus needed was the one at the Earth, between the moon and the sun in the sky, measured at that exact moment of half illumination. He measured it as 87 degrees. The true value is about 89.85 degrees. That sounds like a tiny error, and it is. It's under 3 degrees. But in a right-angled triangle that close to being flat, a tiny error in the angle produces an enormous error in the answer. Aristarchus concluded that the sun was about 19 times further away than the moon. The real ratio is about 390, so he was wrong by a factor of 20. And yet, this is one of the great moments in the history of thought, because of what he did next. If the sun is 19 times further away, and it looks the same size in the sky as the moon does, then the sun has to be 19 times bigger across, which makes it far, far larger than the Earth. And Aristarchus looked at that and drew the obvious conclusion. It made no sense for something enormous to orbit something small. The Earth must go round the sun. Around 270 BC, about 1800 years before Copernicus. On the basis of a measurement that was off by a factor of 20, he got the structure of the solar system right, and almost nobody believed him. Now, the moon itself, that one got solved properly, and much sooner than you'd expect. The man who did it was Hipparchus, working on roads in the 2nd century BC, and his method used something no one else had thought to exploit: a solar eclipse. There was a total eclipse of the sun in 190 BC, total along a track running through the Hellespont, the narrow strait in what's now northwestern Turkey. Observers there saw the sun completely covered. But in Alexandria, well to the south, the same eclipse at the same moment was only partial. About 4/5 of the sun was blocked. Think about why that happens. The moon appears in a slightly different place against the sky depending on where you're standing on Earth. That shift is parallax. Hold a finger up at arm's length and close one eye, then the other, and the finger jumps. Same effect. And the amount it jumps depends on how far away it is. Hipparchus knew the distance between the Hellespont and Alexandria. He knew, from that difference in eclipse coverage, roughly how much the moon had shifted. And he knew, thanks to Eratosthenes a few decades earlier, the size of the Earth itself. That's enough. He put the moon somewhere in the region of 60 Earth radii away. The modern figure is 60.3 Earth radii, which works out to an average distance of 384,400 kilometers. More than 2,100 years ago, working from a shadow crossing 2 cities, someone got the distance to the moon essentially right. It's a strange gap to try to picture. Here's the thing that helps me, and you may have heard it before, but it's worth checking because it sounds like it can't be true. Take all 7 of the other planets in the solar system: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. Line them up side by side, widest diameter to widest diameter, including Jupiter at nearly 140,000 kilometers across. Add it all up, and you get about 380,000 kilometers. Every other planet in the solar system, laid end to end, fits in the space between the Earth and the Moon, with a few thousand kilometers to spare. The Apollo cruise took about 3 days to cross it. Light does it in 1 1/3 seconds, and we know the distance now to a precision that would have made Hipparchus weep. On the lunar surface, at Tranquility Base, and at the Apollo 14 and 15 sites, and at 2 Soviet Lunokhod rover sites, there are arrays of small mirrored prisms sitting in the dust. They've been there for over 50 years. Observatories on Earth fire laser pulses at them and time the return. We know the distance to the moon to within a few millimeters, and we know, from watching that number over decades, that the moon is drifting away from us at about 3.8 centimeters a year. Roughly the rate your fingernails grow. That's the last rung anyone has ever physically crossed. From here on, everything is inference. So let's go outward. And to do that, we have to skip forward about 1700 years, past the fall of Rome and the long, slow preservation of Greek astronomy in the Islamic world, to a Polish canon lying on his deathbed with a freshly printed book in his hands. Nicholas Copernicus died in 1543 in Frombork in what's now northern Poland, and the story goes that the first printed copy of his book reached him on the day he died. The book argued, as Aristarchus had, that the Earth goes round the sun. But Copernicus kept one assumption that turned out to be badly wrong. He assumed the orbits were perfect circles. And because they aren't, his model didn't actually predict planetary positions any better than the old Earth-centered one. It was more elegant. It wasn't more accurate. Fixing that took two men who could hardly have been less alike. The first was Tycho Brahe, a Danish nobleman with a metal prosthetic covering part of his nose, which he'd lost in a duel over a mathematical disagreement. Tycho built an observatory on the island of Hven and spent roughly 20 years measuring planetary positions with the naked eye, night after night, to a precision of about 1 arc-minute. That's a 60th of a degree. Nobody had ever produced data that good, and nobody would produce better until telescopes arrived. The second was Johannes Kepler, a German mathematician with poor eyesight, chronic ill health, and an almost religious conviction that the solar system had to have a hidden mathematical harmony in it. Kepler got hold of Tycho's data after Tycho died in 1601, and he spent years trying to fit the orbit of Mars to a circle. He kept failing by about 8 arc-minutes. 8 arc-minutes is nothing. It's a fraction of the width of a full moon. Almost anyone else would have called that close enough and moved on. Kepler refused. He trusted Tycho's data more than he trusted the circle, and eventually he gave up the circle and tried an ellipse, and it fitted perfectly. That's the first of Kepler's 3 laws, published in 1609. The planets travel in ellipses with the sun at one focus. The second law describes how they speed up when closer and slow down when further away. But it's the third law, which took him another decade and appeared in 1619, that matters for tonight. And the third law is this: take how long a planet takes to complete one orbit and square it. Take its average distance from the sun and cube it. Those two numbers are in a fixed ratio, the same ratio, for every single planet. Which means if you can time an orbit, and timing orbits is easy, you can work out that planet's distance from the sun relative to every other planet. So by 1619, humanity had a complete and accurate map of the solar system. Every relative distance, correct. Jupiter is a bit over 5 times further from the sun than we are. Saturn is a bit over 9.5, and absolutely no idea how big any of it was. It's like being handed a perfect street map of a city with no scale bar printed on it. Every road is in the right place, every junction correct, the whole shape of it exactly right. And you cannot tell whether the thing is a village or a continent. To put a scale bar on that map, you needed one absolute distance. Just one, any single real measurement in real units, anywhere in the system. And Kepler's ratios would instantly convert the entire map into kilometers. Getting that one number took another century and a half, and it cost several people rather a lot. The method came from Edmund Halley, the English astronomer whose name is on the comet. In 1716, he published a proposal, and he was quite clear that he would not live to see it carried out. The idea depends on a rare event called a transit of Venus. Occasionally, Venus passes directly between the Earth and the Sun, and you can watch it cross the face of the Sun as a small black dot taking several hours to traverse. Now, if you watch that from two places far apart on Earth, north and south, you see Venus trace slightly different paths across the solar disk. One observer sees it cut across slightly higher, another slightly lower, which means the crossing takes a slightly different amount of time for each of them. Time the crossing precisely from widely separated places, compare the durations, and the geometry hands you the distance to Venus. Feed that into Kepler's ratios, and every distance in the solar system converts into real units at once. There was one problem. Transits of Venus come in pairs 8 years apart, and then don't happen again for over a century. Halley knew the next pair would arrive in 1761 and 1769. He was born in 1656. He was not going to be there. So he wrote it down as instructions for a generation not yet born and asked them to organize it. And they did. What followed in 1761 and 1769 was arguably the first global scientific collaboration in history. Hundreds of observers from Britain, France, Russia, Sweden, Denmark, the American colonies, and elsewhere traveled to remote observing sites across the planet, many of them at genuine risk, several of them through active war zones, in a coordinated attempt to time a small black dot crossing the Sun. Britain sent Charles Mason and Jeremiah Dixon, who would later go on to survey the boundary line in North America that carries their names. Russia coordinated observations across Siberia. The Royal Society sent an expedition to the island of St. Helena in the South Atlantic. And in 1769, the Royal Navy fitted out a ship called the Endeavour under a lieutenant named James Cook and sent it round Cape Horn to Tahiti. The observing site is still called Point Venus today. Cook's Pacific voyage, the one that ended up charting New Zealand and the eastern coast of Australia and changing the history of that entire part of the world, existed in the first place because somebody needed to time a transit. But the story that stays with people is Guillaume Le Gentil. Le Gentil was a French astronomer, and he left Paris in March 1760, more than a year ahead of the transit, bound for Pondicherry on the southeastern coast of India. Plenty of time, except France and Britain were at war. His ship was diverted. Pondicherry fell to the British. He was still at sea on the 6th of June 1761 when the transit happened, and the sky was perfectly clear, and he could see Venus crossing the Sun beautifully, and it was completely useless because you cannot take a precise timing measurement from the rolling deck of a ship. So he made a decision. Rather than go home, he would simply wait for the second transit, 8 years away. He spent those 8 years in the Indian Ocean region, mapping coastlines, doing natural history, waiting. He eventually settled at Pondicherry, which had been returned to France, and built a small observatory there specifically for the event. He tested his instruments for months. The weather in the preceding weeks was reportedly flawless. On the 3rd of June 1769, the morning of the transit, a cloud arrived and sat over Pondicherry for the duration. He saw nothing. He then got dysentery, was delayed further, was shipwrecked on the way back, and finally reached Paris in October 1771, 11.5 years after leaving. He found that he had been declared legally dead. His estate had been divided among his relatives. His seat at the Academy of Sciences had been given to someone else. His wife had remarried. He did eventually get the seat back, and he remarried, and by most accounts lived reasonably contentedly for another 20 years. But it's hard to think of anyone who has ever wanted a number more. The number itself, when all the observations were finally reduced and combined, came out at around 153 million kilometers. The modern value for the average distance from the Earth to the Sun is 149,597,8 871 kilometers. Since 2012, it's been defined as an exact figure rather than measured, and it has a name: the astronomical unit. 18th century astronomers, with wooden telescopes and pendulum clocks and no way to communicate faster than a sailing ship, got it right to within about 2.5%. And the moment they had it, Kepler's beautiful scaleless map snapped into real size. Jupiter went from being 5.2 units out to being 778 million kilometers out. Saturn to 1.4 billion. The solar system stopped being a diagram and became a place. Now, while all of that was being organized, something else had already been quietly settled, almost by accident, nearly a century earlier. In 1676, a Danish astronomer named Ole Romer was working at the Paris Observatory, and he was studying the moons of Jupiter, specifically Io, the innermost of the four large ones, which orbits Jupiter every 42.5 hours and disappears into Jupiter's shadow each time round. Those eclipses of Io are a clock, a very regular, very visible clock hanging in the outer solar system, which made them extremely useful, because if you could predict when Io would vanish, and you observed the actual moment it vanished from wherever you happened to be standing, the difference would tell you your longitude. Longitude at sea was the great, unsolved practical problem of the age. So people cared about Io's timetable a great deal, and Romer noticed something wrong with it. The eclipses ran late, not randomly, systematically. When the Earth was on the far side of its orbit from Jupiter, Io's eclipses came consistently later than predicted. When the Earth swung round to the near side, they came consistently early. The whole schedule drifted back and forth over the course of a year by about 22 minutes. Everyone else had treated this as an annoying imperfection in the moon's motion. A moon that runs late is a badly behaved moon, and badly behaved moons are somebody else's problem. Romer looked at it and asked a different question. What if Io is perfectly punctual and the light is late? Because if light takes time to travel, then when the Earth is further from Jupiter, the light has further to go, and the eclipse looks delayed simply because the news of it takes longer to arrive. The 22 minutes wouldn't be Io misbehaving. It would be the time light needs to cross the diameter of the Earth's orbit. That's the first demonstration in history that light has a finite speed. Before Romer, plenty of serious people, including Kepler and Descartes, had assumed light was instantaneous. His figure of about 22 minutes was a bit high. The real crossing time is roughly 16 minutes and 40 seconds. But the conclusion was right, and the reasoning was right, and Christian Huygens took Romer's timing, combined it with the best available estimate of the solar system's size, and produced the first actual speed. He got somewhere around 220,000 kilometers per second, which is low, but it is unmistakably the right order of magnitude from a man in the 1670s watching a moon go behind a planet. It got refined steadily after that. James Bradley found a completely independent method in 1729 using the way starlight appears to tilt because the Earth is moving, and got about 301,000. Hippolyte Fizeau measured it in a Paris suburb in 1849 by shining light through the teeth of a spinning wheel at a mirror 5 miles away. Léon Foucault improved on it with rotating mirrors. Albert Michelson spent decades of his life refining it, firing light between mountaintops in California, and the modern figure is not measured at all anymore. It's defined. Since 1983, the speed of light in a vacuum is exactly 299,792,458 meters per second, and the meter itself is now defined backwards from that. We decided the speed of light was the more fundamental thing, and built the ruler out of it. which gives us the unit that carries the rest of this journey. A light year is simply how far light travels in 1 year. 9.46 trillion kilometers. It's a distance, not a time, despite the name, and people mix that up constantly. For scale, light circles the entire Earth 7.5 times in 1 second. It reaches the moon in 1 1/3. It takes 8 minutes and 19 seconds to arrive from the sun, so the sunlight on your skin in the afternoon left before you'd finished lunch. It takes about 5.5 hours to reach Neptune. And a light year is longer than all of that put together by an enormous margin. Which is why, when someone finally managed to measure the distance to another star, the number came as a genuine shock. The method for reaching the stars had been obvious for 2,000 years. It was doing it that turned out to be nearly impossible. The idea is the same finger trick from earlier. Hold up a finger, blink one eye and then the other, and it jumps against the background. The Earth gives you a much bigger version of that. In January, you're on one side of your orbit, and in July, you're on the other, 300 million kilometers away. That's an enormous baseline. So a nearby star, viewed in January and again in July, should appear to shift very slightly against the more distant stars behind it. Measure that shift, and simple triangulation gives you the distance. So why did it take until 1838? Astronomers had understood this since antiquity, and that's precisely why most of them rejected the idea that the Earth moves at all, because they looked carefully for centuries, and the stars did not shift, not by any amount anyone could detect. There were only 2 possible explanations. Either the Earth was sitting still, or the stars were so unimaginably far away that the shift was too small to see. Almost everyone took the first option. It seemed more reasonable. So which was it? Were they standing still, or was the sky simply further away than anyone could stomach? They took the first option, and they were wrong, and the reason they were wrong is worth appreciating. The shift they were looking for is genuinely tiny. For the very nearest stars, it is under 1 second of arc. A second of arc is 1/3600th of a degree. It is roughly the width of a coin seen from 4 kilometers away. Tycho Brahe, the finest naked-eye observer who ever lived, could measure to about 1 arc minute. He needed to be 60 times better. So the hunt went on for a very long time. Robert Hooke tried and failed. James Bradley went looking for parallax in the 1720s and instead accidentally discovered stellar aberration, which is a real effect, and did prove the Earth moves, just not the one he was after. William Herschel spent years on it. Everyone failed. It finally broke in the late 1830s, and it broke in 3 places almost at once. The man who got there first, and got there cleanly, was Friedrich Bessel, working at the observatory in Königsberg in East Prussia. And Bessel made one very smart decision before he started. He didn't pick a bright star. Everyone assumed bright meant close, and that's a reasonable assumption that happens to be unreliable, because a star can be bright either because it is near or because it is enormous. Bessel picked his target on a better criterion. He chose a faint, unremarkable double star in the constellation Cygnus called 61 Cygni for one reason. It moved. Stars drift very slowly across the sky over decades, and 61 Cygni drifted faster than almost anything known. That's proper motion, and a large proper motion is a much better hint of closeness than brightness is. It's the same reason a nearby car appears to sweep past you while a distant aircraft appears to crawl. Bessel observed it for over a year with a superb new instrument, a heliometer built by the Munich optician Joseph Fraunhofer, which split the image in 2 and let him measure tiny angular separations far more precisely than anyone had managed before. In 1838, he announced a parallax of about 1/3 of an arcsecond. which put 61 Cygni at roughly 10 light-years away. Take a moment with that number, because in 1838 it was almost offensive. The distance from the Earth to the Sun had only recently been pinned down at 150 million kilometers, and that had felt vast. Bessel's star was about 660,000 times further away than that. Nothing in human experience prepares you for a jump like that, and there was no reason to think 61 Cygni was anything special. It was a dim little double star that nobody had cared about. If the boring ones are 10 light-years out, the sky was suddenly a very different place. Thomas Henderson, working from the Cape of Good Hope, had actually measured Alpha Centauri earlier, but published later, in 1839, and his star turned out to be closer still. Friedrich Struve in Dorpat published a figure for Vega around the same period, less reliably. Modern measurements put 61 Cygni at about 11.4 light-years, so Bessel was a little low, but broadly right. Alpha Centauri sits at 4.37 light-years, and the nearest star to the Sun of all, a faint red dwarf called Proxima Centauri, that isn't visible without a telescope, is 4.24 light-years away. That's the closest neighbor we have. And it's worth converting, because light-years stop meaning anything after a while. 4.24 light-years is about 40 trillion kilometers. Voyager 1, launched in 1977, and now the most distant human object in existence, is traveling at roughly 61,000 kilometers per hour. It is not going to Proxima, but if it were, it would take somewhere in the region of 70,000 years. That's the nearest one. Parallax also gave astronomers their natural unit, which is why you'll hear it constantly. A star with a parallax of exactly 1 arcsecond sits at a distance of 1 parsec. The name is just a compression of parallax and arcsecond. A parsec is 3.26 light-years, and no star is that close, which tells you something all on its own. So by around 1840, the situation was this. The solar system was measured. A handful of nearby stars were measured. And the parallax method had a hard ceiling, because beyond a few hundred light-years, the shift becomes too small for any 19th century instrument to catch, which left the largest question completely open. What is all of this part of, and how big is that? The first person to seriously try to map it was William Herschel, working in England in the 1780s with his sister Caroline, who was an extraordinary observer in her own right, and discovered 8 comets. Herschel built the finest telescopes in the world in his own workshop, and in 1785 he attempted something nobody had tried. He counted stars. He called it star gauging. He would point his telescope at a patch of sky, count every star he could see in that patch, then move to another patch and do it again, hundreds of times over. His reasoning was straightforward. If stars are spread evenly through space, then directions with more stars are directions where the system extends further. And the pattern he found was clear. Enormous numbers of stars along the band of the Milky Way, far fewer looking perpendicular to it. So the system is flattened. A disk. We're inside a disk, and when we look along its plane, we see stars piled up behind stars, and when we look out of the plane, we see comparatively few, and then nothing. That is correct, and it's a beautiful piece of work. Herschel then made one wrong assumption that nobody could have avoided. He assumed he could see all the way to the edge in every direction, and that starlight travels through space unimpeded. It doesn't. The galactic disk is full of dust. Interstellar dust dims and reddens starlight, and along the plane of the Milky Way, it becomes thick enough that beyond a few thousand light-years, you simply cannot see through it. So what was he actually measuring? Herschel wasn't measuring the edge of the galaxy. He was measuring the distance at which the dust closed in, and the dust closes in at roughly the same distance in every direction along the disk, which produced a map with the sun sitting almost exactly at the center. That error stood for well over a century, and it was finally overturned by a young American astronomer named Harlow Shapley, working at Mount Wilson in California around 1918. And Shapley's insight was to stop looking at individual stars and start looking at globular clusters. Globular clusters are dense spherical swarms, each containing hundreds of thousands of ancient stars, and crucially, they sit above and below the dusty plane of the galaxy, out in the clear. You can see them from a very long way off. Shapley mapped where they were, and they were not distributed evenly around us at all. The overwhelming majority sat in one direction, towards the constellation Sagittarius. His conclusion was that the clusters swarm around the true center of the galaxy, and the true center is off in Sagittarius, tens of thousands of light years away, and the sun is nowhere near it. He was right. The sun sits about 26,000 light years out from the galactic center, in a fairly ordinary stretch of one of the spiral arms. So within about 130 years, we had gone from the Earth at the center of everything, to the sun at the center of everything, to the sun as an unremarkable star, well out in the suburbs of a disk 100,000 light years across. And it's worth pausing here before we go further out, because we now know a great deal about the galaxy Shapley was fumbling towards, and it's a strange and beautiful object. The Milky Way is a barred spiral, a flattened disk roughly 100,000 light years across and about 1,000 light years thick through the main body, which makes it about 100 times wider than it is deep. Proportionally, it's shaped something like a vinyl record. Somewhere between 100 and 400 billion stars, depending on how you count the very faint ones, which are the majority and are extremely hard to survey. The stars are arranged in arms, not solid structures, more like traffic jams, density waves moving through the disk, where gas piles up and compresses and triggers new star formation, which is why the arms look bright. The individual stars drift in and out of them over time. The major ones have names: Perseus, Sagittarius, Scutum Centaurus, Norma. We're not in a major arm. The sun sits in a smaller structure called the Orion Spur, sometimes called the local arm, a sort of bridge between two of the big ones, about 26,000 light years from the center, roughly halfway out. And we are moving. The sun orbits the galactic center at something like 230 kilometers per second, which sounds tremendous until you divide it into the circumference. One complete orbit takes about 230 million years. That period is called a galactic year, which gives you a rather good unit for deep time. The sun has completed about 20 galactic years since it formed. The last time the sun was in this position relative to the galactic center, the first dinosaurs were appearing. 2 galactic years ago, there was no life on land at all. At the center, hidden completely behind the dust that fooled Herschel, is something we could not see for most of the 20th century. Radio astronomers found a compact, intensely bright source there in 1974 and gave it the slightly awkward name Sagittarius A star. But radio brightness alone doesn't tell you what something is. What settled it was 2 teams, one led by Reinhard Genzel in Germany and one by Andrea Ghez in California, who spent decades doing something conceptually simple and technically brutal. They watched individual stars near the galactic center in infrared light which penetrates the dust and tracked their positions year after year after year. And those stars are not drifting, they're orbiting something. One of them, cataloged as S2, completes a full orbit in about 16 years, and at its closest approach, It is moving at nearly 8,000 kilometers per second. Watching a star whip round like that lets you calculate the mass it's orbiting with real precision, in exactly the same way Kepler's laws work for planets. The answer is about 4.3 million times the mass of the Sun, packed into a region smaller than the orbit of Mercury. What packs 4 million suns into a space smaller than one planetary orbit and gives off almost no light? There is nothing that can be except a black hole. Genzel and Ghez shared the Nobel Prize for it in 2020, and in May 2022, the Event Horizon Telescope, a network of radio dishes spread across the planet and combined to act as a single instrument the size of the Earth, released an actual image of it. A dim orange ring around a dark center, 26,000 light-years away, at the middle of the galaxy we live in. There's one more local detail worth knowing, because it's genuinely peculiar. The Sun is currently sitting inside a hole. The space around us for roughly 1,000 light-years in most directions is unusually empty. Hot, thin gas, far below the normal density of the interstellar medium. It's called the local bubble, and the best current explanation is that a series of supernovae, perhaps 14 million years ago, blew the gas out of this region and left a cavity behind. The Sun wandered into it a few million years ago and is passing through, which is a small reminder that even the quiet spaces have a history. Beyond the disk, there's a sparse halo of ancient stars and globular clusters, the ones Shapley used, extending out several 100,000 light-years. And further out again, invisible and inferred entirely from its gravitational effect on how fast the outer parts of the galaxy rotate, there is a vast halo of dark matter, which probably outweighs everything visible by a factor of 5 or more. That was worked out largely by Vera Rubin in the 1970s, measuring rotation curves of galaxies and finding that the outer regions were turning far too fast for the visible mass to hold them together. She never received a Nobel Prize either. So that's home. 100,000 light-years of stars, turning slowly, with a 4 million solar mass black hole at the center, embedded in a much larger cloud of something nobody has identified. And at that point, the argument that had been rumbling for 2 centuries finally came to a head. Because there was one more question, and it was the biggest one anybody had ever asked. The question was about the spiral nebulae. Astronomers had been cataloging faint, fuzzy patches of light for a long time. Charles Messier compiled a famous list of them in the 1770s, largely so that comet hunters would stop mistaking them for comets. Some resolved into star clusters when you looked harder. Some were clouds of glowing gas. But a particular subset had a distinctive spiral structure, like water going down a drain, and nobody could agree what they were. There were 2 positions, and they could not both be right. The first was that the spiral nebulae were relatively nearby clouds of gas inside our own galaxy, possibly solar systems in the process of forming, which would mean the Milky Way is the entire universe, and it has some interesting objects in it. The second was that each spiral nebula was itself an entire galaxy, comparable to the Milky Way, unimaginably far away, and that the universe contains vast numbers of them. Immanuel Kant had floated this in 1755 and given it a name that is still the best phrase anyone has come up with. Island universes. So which one is it? Is the Milky Way everything there is, or is it one of countless others? The gap between those 2 answers is the largest single gap in the history of measuring anything. It is the difference between a universe 100,000 light-years across and a universe with no known limit at all. In April 1920, at the Smithsonian in Washington, Harlow Shapley and Heber Curtis stood up and argued it out in front of an audience. It's remembered as the Great Debate. Shapley argued for one enormous galaxy. Curtis argued for island universes. Both men made good points, both made errors, and nobody won because the debate could not be settled by argument. It needed a distance, and parallax was useless at those ranges by a factor of thousands. What broke it open had already been published 8 years earlier by a woman working in a basement room at Harvard for 30 cents an hour. Her name was Henrietta Leavitt. She was born in Massachusetts in 1868, studied at what became Radcliffe College, and lost most of her hearing to an illness in her 20s. She joined the Harvard College Observatory as one of a group of women employed by the director, Edward Pickering, to examine photographic plates. They were called computers because computing was a job description before it was a machine. They were paid less than the unskilled laborers who maintained the buildings. They were largely not permitted to operate the telescopes. Their work was to sit with glass photographic plates and measure and catalog the stars recorded on them, thousands upon thousands of them, by hand. Leavitt was assigned to variable stars that change in brightness over time. She concentrated on a particular type called Cepheid variables, named after the star Delta Cephei. Cepheids pulse. They physically swell and contract, brightening and dimming in a smooth, utterly reliable cycle that can run anywhere from a day or so to a couple of months. Set your watch by them. And she studied Cepheids in a specific place, the Small Magellanic Cloud, a hazy patch visible from the southern hemisphere, which nobody at the time understood. That choice is the whole thing, because whatever the Small Magellanic Cloud was, every star in it sat at essentially the same distance from Earth. They were all in the same clump, which meant that if one of them looked brighter than another, it genuinely was brighter. The usual confusion between a near-dim star and a distant bright one simply didn't apply. Leavitt cataloged their periods and their brightnesses, and in a short paper in 1908, expanded into a decisive one in 1912 with 25 Cepheids in it. She reported what she'd found. The brighter ones took longer to pulse. And not vaguely. The relationship was tight, clean, and mathematical. Plot period against brightness, and the points fall on a line. Now think about what that gives you. If the period tells you the true brightness, then you can point a telescope at any Cepheid anywhere, time its pulse, and know how much light it is actually producing. Then you compare that with how bright it appears from here. And light dims in a completely predictable way with distance, falling off with the square of it. Something twice as far away appears 4 times fainter. True brightness plus apparent brightness equals distance. That's a standard candle. It's the single most important idea in the measurement of the universe. Find an object whose real luminosity you can determine independently, and it becomes a distance marker anywhere you can see it. Parallax reaches a few hundred light years. Cepheids reach millions. Leavitt found the key that unlocked the cosmos, and she was not permitted to use it. Pickering directed her to continue with the stellar magnitude work she was assigned. She did other important things, including establishing a photographic brightness standard used worldwide, and she died of cancer in 1921 at 53. In 1926, the Swedish mathematician Gösta Mittag-Leffler began preparing to nominate her for the Nobel Prize and wrote to Harvard for details of her work. He was informed that she had been dead for 4 years. The prize is not awarded posthumously. The man who picked up her key was Edwin Hubble. Hubble was, by most accounts, not an especially easy person. He was a lawyer by training, an accomplished amateur boxer, and he affected a British accent and a pipe after a period at Oxford, neither of which endeared him to his American colleagues. He was also a superb observer with access to the best instrument on the planet. That instrument was the 100-inch Hooker telescope at Mount Wilson, above Los Angeles, which from 1917 was the largest telescope in the world. In October 1923, Hubble was photographing the Andromeda Nebula, the largest and brightest of the spirals, looking for novae. On one plate, he found what he took to be 3 novae and marked them N. Then he went back over earlier plates of the same region and realized that one of them wasn't a nova at all. It was brightening and dimming in a repeating cycle. It was a Cepheid. On that glass plate, which still exists in the Carnegie archives, you can see where he struck out the letter N and wrote in red ink, with an exclamation mark, the word VAR. He had a standard candle inside Andromeda. He timed its period, applied Leavitt's relation, and got a distance. He calculated roughly 900,000 light-years. Shapley's entire Milky Way, the largest structure anyone had proposed, was about 300,000 light-years across in Shapley's own generous estimate. Hubble's Cepheid was 3 times that distance on its own. Andromeda was not in our galaxy. It was not anywhere near our galaxy. It was another galaxy, a separate island of hundreds of billions of stars, and every one of those faint spirals scattered across the sky was another one. Hubble sat on the result for over a year, checking it. He announced it formally on the 1st of January 1925, in a paper read out in his absence at a meeting of the American Astronomical Society. Shapley, when he was shown the letter containing the result, is reported to have said that it had destroyed his universe. And Hubble's number was actually too small, by a factor of nearly 3. He had no way of knowing it, but there are 2 distinct populations of Cepheids with slightly different period luminosity relations, and he was unknowingly comparing one type against a calibration built from the other. Walter Baade sorted this out at Mount Wilson in 1952, and the distances all roughly doubled overnight. The modern figure for Andromeda is about 2.5 million light-years, which means the light arriving from it tonight left before anything you would call a human being existed. Our ancestors at that point were early Australopithecus, walking upright in East Africa, not yet making stone tools, and you can see it with your own eyes. On a genuinely dark night, away from towns, Andromeda is visible without any equipment at all, as a faint, elongated smudge in the autumn sky. It is the most distant object the unaided human eye can perceive, and there is something quietly staggering about the fact that a photon can cross 2.5 million light-years of nothing and end its existence on the back of your retina. So by 1925, the universe had expanded from one galaxy to an unknown number of them. And the very next question was what all those galaxies were doing. The answer to that turned out to be considerably stranger than anyone had prepared for. The clue had been sitting in the data for over a decade, and it came from a quiet astronomer in Arizona who has never received anything like the credit he deserves. Vesto Slipher worked at the Lowell Observatory in Flagstaff, and from about 1912 he was doing something extremely difficult. He was taking spectra of the spiral nebulae. A spectrum is what you get when you spread starlight out into its colors, and a spectrum isn't a smooth rainbow. It's crossed by dark lines at very specific colors where particular elements in the star have absorbed particular wavelengths. Hydrogen leaves a signature. Calcium leaves a signature. Those line patterns are fixed by physics, and they are identical everywhere in the universe, which makes them a reference mark. If you know exactly what color a hydrogen line is supposed to be, and you find it sitting at a different color, something has shifted it, and motion shifts it. It's the same effect you hear when an ambulance passes and the siren drops in pitch as it goes by. Approaching, the waves get compressed and the pitch rises. Receding, they get stretched and it falls. Light does the same thing. An object moving towards you has its spectral lines pushed towards the blue end. An object moving away has them stretched towards the red. Slipher's plates took entire nights of exposure, sometimes several nights stacked together, because the nebulae were so faint. And what he found, over and over, was redshift. By 1917, he had spectra for 25 spiral nebulae. 21 of them were moving away from us, some at over 1,000 kilometers per second, far faster than anything else known. Nobody could make sense of it, including Slipher. Why would almost everything be running away from us specifically? What could possibly be so objectionable about this particular corner of the cosmos? The person who worked out what it meant was a Belgian priest. Georges Lemaitre was ordained as a Catholic priest and also held a doctorate in physics from MIT. And in 1927, he published a paper that solved Einstein's equations of general relativity for a universe that isn't static. He showed the equations naturally describe a universe that expands. He connected that expansion directly to Slipher's redshifts, and he even estimated how fast it was happening. The paper appeared in French, in a small Belgian scientific journal, and it was almost entirely ignored. Lemaitre took it to Einstein personally at a conference in Brussels. Einstein's response, by Lemaitre's own account, was that the mathematics was correct, but the physics was terrible. Einstein had good reason to be uncomfortable. His own equations had told him the same thing years earlier, that a universe under gravity cannot sit still, and he had disliked that answer so much that he inserted an extra term to hold it in place. He called it the cosmological constant. It was there purely to keep the universe from moving. 2 years later, in 1929, Edwin Hubble published the observation that settled it. Hubble had what Slipher lacked, which was distances. He'd been finding Cepheids in nearby galaxies and building up a distance list, so he could take Slipher's velocities, pair them with his own distances, and simply plot one against the other. The points fell on a straight line. The further away a galaxy was, the faster it was receding, and the relationship was proportional. Twice as far, twice as fast. 10 times as far, 10 times as fast. That is Hubble's law, and there is only one sensible reading of it. Because here is the thing that trips almost everyone up, and it's worth going slowly. This is not galaxies flying outward through space from some explosion, with us near the middle. If it were, the pattern wouldn't be a clean proportion, and we'd have to be in a very special location. It's space itself expanding, everywhere, all at once. Picture a loaf of raisin bread rising in an oven. The raisins aren't moving through the dough. The dough is swelling, and every raisin is getting further from every other raisin. Now sit on any raisin you like and look around. A raisin 2 centimeters away has 2 centimeters of dough between it and you, and that dough is expanding. A raisin 10 centimeters away has 5 times as much dough between you, expanding 5 times as much, so it recedes 5 times faster. Every raisin sees exactly what Hubble saw, and no raisin is at the center, because there isn't one. That's the universe. There is no point you can travel to and say the expansion started here. It started everywhere, and it's still going on in the space between the galaxies right now, including the space above your roof. Lemaitre took it to the obvious conclusion. If everything is getting further apart, then run the film backwards and everything was closer together. Go back far enough, and the whole observable universe was compressed into something very small and very hot. He called it the primeval atom. The name that stuck came from an opponent. Fred Hoyle, a British astronomer who preferred a steady-state universe with no beginning, referred to the idea on BBC Radio in 1949 as this Big Bang. He meant it dismissively. It is now the standard term in every textbook on Earth, which is a fate Hoyle presumably found irritating for the rest of his life, and it gave the universe something it had never had before: an age. If you know how fast everything is separating, you can calculate how long ago it was all together. Hubble's original number gave about 2 billion years, which was immediately a disaster, because geologists already knew from radioactive dating that rocks on Earth were older than that. The universe cannot be younger than its contents. That problem took until the 1950s to fix, when Walter Baade sorted out the two Cepheid populations and Alan Sandage refined the calibration, and all the extragalactic distances stretched out. The age stretched with them. The current figure, and it comes from several completely independent lines of evidence that agree, is 13.8 billion years. So now we have a universe with a size and a beginning and a rate of expansion. What we still haven't done is look at how the galaxies in it are arranged. And they are not scattered at random, not remotely. Start close and work out. The Milky Way has satellites. The two largest are the Magellanic Clouds, visible from the southern hemisphere as detached fragments of the Milky Way, and they sit around 160,000 and 200,000 light-years out. There are also a couple of dozen faint dwarf galaxies orbiting us, most of them so sparse they were only found by careful statistical work on survey data. Zoom out, and the Milky Way is one of two dominant members of a small collection called the Local Group. It contains somewhere over 80 known galaxies, spread across roughly 10 million light-years, and almost all of them are dwarfs. The Milky Way and Andromeda hold most of the mass, with the Triangulum galaxy a distant third. And Andromeda is the one galaxy in the sky that is not receding from us. It's approaching at about 110 kilometers per second, because at this range, mutual gravity beats the expansion of space comfortably. In roughly 4.5 billion years, the two will collide. Not with any crashing, because the space between stars is so vast that essentially no stars will hit each other. The galaxies will pass through one another, tear each other's spiral structure apart over hundreds of millions of years, and eventually settle into a single large elliptical galaxy. People have started calling it Milkomeda, which is a terrible name that appears to be sticking. Zoom out further. The Local Group sits on the outskirts of something much larger. About 54 million light-years away lies the Virgo cluster, containing somewhere between 1,000 and 2,000 galaxies bound together by gravity, with the giant elliptical M87 near its heart. M87 holds the supermassive black hole that became the first ever directly imaged, released in 2019 as that orange donut of light. Our entire Local Group is falling towards Virgo. Zoom out again, and it keeps going. In 2014, a team led by Brent Tully mapped the motions of tens of thousands of galaxies and found that our region belongs to a single enormous flow pattern, a supercluster around 520 million light-years across containing something like 100,000 galaxies. They named it Laniakea, from Hawaiian, meaning immense heaven. And at the largest scales, the arrangement becomes genuinely beautiful. Galaxies are not sprinkled evenly. They lie along filaments, long, thin strands of galaxies, threading through space, meeting at dense knots where the great clusters sit, spreading into vast flat sheets. Astronomers call it the cosmic web, and it looks unnervingly like a network of neurons, or the mycelium of a fungus. Between the filaments are the voids, and the voids are enormous and nearly empty. The Bode's void, found in 1981, is a roughly spherical region about 330 million light-years across, containing only a few dozen known galaxies. It should contain thousands. If the Milky Way sat at the center of it, we would not have discovered other galaxies existed until well into the 20th century, because there would have been nothing close enough to see. Most of the universe, by volume, is void. The bright structures are the thin walls between the empty rooms. To map any of that, though, you need to keep climbing, and Cepheids give out. Even with the Hubble Space Telescope, individual Cepheid variables can only be picked out of the general glow of a galaxy to a distance of roughly 100 million light-years. Past that, they blend into everything else. And 100 million light-years, which sounded enormous a few minutes ago, doesn't get you out of the local neighborhood. So you need a brighter candle. Much brighter. And the one the universe supplies is spectacular. To understand it, you have to start with what happens to an ordinary star at the end. A star like the Sun spends most of its life fusing hydrogen, eventually swells into a red giant, and then sheds its outer layers into space. What's left behind is the exposed core. Carbon and oxygen, no longer fusing anything, roughly the mass of the Sun packed into a sphere about the size of the Earth. That's a white dwarf, and the density is difficult to hold in your head. A teaspoon of white dwarf material weighs something in the region of a ton. What stops it collapsing further isn't heat, because it's dying. It's a quantum mechanical effect called electron degeneracy pressure, which comes down to electrons refusing to occupy the same state as each other. They resist being pushed together, and that resistance holds the star up. But that resistance has a limit. The man who found the limit was Subrahmanyan Chandrasekhar, and he worked it out in 1930 during the voyage from Madras to England at the age of 19, on his way to start at Cambridge. He calculated that above about 1.4 times the mass of the Sun, electron degeneracy pressure loses. The star cannot hold itself up. When he presented this in London, Arthur Eddington, the most eminent astrophysicist in Britain, publicly ridiculed it. Chandrasekhar was right. He received the Nobel Prize for it in 1983, 53 years later. Now here's why that limit matters for measuring the universe. Most stars come in pairs, so a white dwarf often has a companion star right beside it. And if that companion swells up in its own old age, the white dwarf can begin pulling material off it, siphoning gas across the gap and adding it to itself. It gains mass, slowly, and it climbs towards 1.4 solar masses. So what happens when it gets there? And when it crosses that line, the support fails, the core compresses, carbon fusion ignites through the entire star in a couple of seconds, and the whole object detonates, completely. Nothing is left behind. That's a type Ia supernova, and for a few weeks it shines with roughly 5 billion times the luminosity of the Sun. A single dying star briefly outshining every other star in its galaxy combined, which is useful enough. But the crucial part is the trigger. Because the explosion always happens at the same mass, the amount of fuel is always the same, and so the brightness is very nearly always the same. A standard candle you can see across billions of light years. They aren't perfectly identical, and that got sorted out too. In the early 1990s, Mark Phillips showed that the brighter ones fade more slowly, in a predictable way, so you can watch the decline curve and correct for the difference. Once you do that, they become extraordinarily precise. So in the mid-1990s, two rival teams set out to use them to answer a specific question. Everyone assumed the expansion of the universe must be slowing down because gravity pulls, and all that matter must be applying a brake. The question was how hard the brake was, because that determines whether the universe expands forever or eventually collapses back. One team was the High Z supernova search team, led by Brian Schmidt, with Adam Rees doing much of the analysis. The other was the Supernova Cosmology Project under Saul Perlmutter. They were competing hard. In 1998, both teams announced the same result, independently, and neither of them wanted it. The distant supernovae were too faint. Consistently, which meant they were further away than they should be, which meant the universe had expanded more in the intervening time than any decelerating model allowed. The expansion is not slowing down. It has been speeding up for roughly the last 5 billion years. Something is pushing space apart, and it overwhelms the gravity of everything in it. Nobody knows what it is. The placeholder name is dark energy, which is an honest label for an admission of ignorance. And the mathematics that describes it turns out to be almost exactly the term Einstein invented in 1917 to hold the universe still and then abandoned in embarrassment. Perlmutter, Schmidt, and Rees shared the Nobel Prize in 2011, and it changed the inventory of the universe completely. Add it all up, and ordinary matter, the kind that makes atoms and planets and people, is about 5% of what's out there. Dark matter, which has mass and gravity, but doesn't interact with light and hasn't been identified, is about 27%. And dark energy is the remaining 68%. Everything in this entire story, every star and galaxy and cluster, is happening in the 5%. There's one more thing worth mentioning here, because it's the live problem in cosmology right now. Measure the expansion rate using the distance ladder, Cepheids into supernovae, and you get about 73 kilometers per second per megaparsec. Measure it a completely different way from the early universe, and you get about 67.4. Those two numbers should agree. They don't, and the gap is far larger than the uncertainties. It's called the Hubble tension, and it has been getting worse as both measurements have improved. Either somebody has a subtle error nobody has found, or there is something missing from our model of the universe. It is genuinely unresolved tonight, which brings us to that second way of measuring and to the last rung on the ladder. Because past the supernova, there is one more thing to see, and it is the oldest light there is. Go back far enough, and the universe was hot, not warm, hot enough that atoms could not exist. For the first few 100,000 years, everything was a plasma, bare atomic nuclei and free electrons, all charged, all packed together, and light cannot travel through that. Photons scatter off free electrons almost immediately, ricochet, scatter again. The early universe was opaque, glowing brilliantly and completely impenetrable, like being inside a fog bank lit from all directions. Then it expanded, and expanding gas cools. About 380,000 years after the beginning, the temperature fell to somewhere around 3,000 degrees, and at 3,000 degrees, electrons finally moved slowly enough to be captured and held by protons. Atoms formed, neutral hydrogen, everywhere, all at roughly the same moment, and the fog lifted. With the free electrons gone, there was nothing left to scatter off, and light could suddenly travel in a straight line. Every photon that happened to be flying at that instant simply carried on going. They are still going. They have been traveling, unimpeded, for 13.8 billion years. That light was orange and hot when it was released, but it has been stretched by the expansion of space the entire time it has been in flight, its wavelength growing along with everything else, by a factor of about 1100. So it has slid down out of the visible range, through infrared, into microwaves. It arrives now as a faint uniform glow filling the whole sky, corresponding to a temperature of 2.7 degrees above absolute zero. It is called the cosmic microwave background, and it was found completely by accident. In 1964, two radio astronomers at Bell Labs in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for radio astronomy. And they had a problem, a persistent low hiss they could not get rid of. It came from every direction, day and night, all year, and it did not change no matter where they pointed. They checked everything. They rebuilt connections. And they discovered that a pair of pigeons had nested inside the horn and coated the interior in droppings, which Penzias later described in a memorably clinical phrase as a white dielectric material. They evicted the pigeons, They cleaned the antenna thoroughly. The hiss remained exactly as it was. Meanwhile, about 50 kilometers away at Princeton, a group under Robert Dicke had worked out theoretically that if the Big Bang happened, there ought to be leftover radiation at just a few degrees above absolute zero, and they were building an instrument to look for it. Someone eventually put the two groups in touch. Dicke reportedly put down the phone and told his team they had been beaten to it. Penzias and Wilson received the Nobel Prize in 1978 for detecting, as an unwanted noise in an antenna they were trying to clean, the afterglow of the beginning of the universe. If you're old enough to remember analog television, a small fraction of the static on an untuned channel was this: photons from 380,000 years after the Big Bang, ending their journey in a set-top aerial in someone's living room. The COBE satellite mapped it properly from 1989 and found something crucial. The glow is not perfectly smooth. There are faint variations, warmer and cooler patches, at the level of about 1 part in 100,000. And what are those wrinkles? Those wrinkles are the seeds. Slightly denser regions in the infant universe, which gravity then spent 13 billion years amplifying into filaments and clusters and galaxies and stars. Every structure in the cosmic web grew from those tiny mottled patches. You are looking at a baby photograph of everything, taken before it had any features at all. And that glow is where the ladder ends. Not because we have run out of cleverness, but because there is nothing behind it to see. Before 380,000 years, the universe was opaque. No light escaped. So no telescope, however good, however far in the future, will ever produce an image of anything earlier, because there are no photons from earlier to collect. Astronomers call it the surface of last scattering, and that phrase is worth taking apart, because it clears up the single most common confusion about all of this. It is not a place. It is not a wall standing somewhere out there in space at a fixed location. It's the boundary of what light has had time to reach us from. And because the universe has a finite age and light has a finite speed, there is simply a limit to how far away something can be and still have got a signal to us. Beyond that limit, whatever is there, its light is still in transit. It has not arrived yet. That boundary is called the particle horizon, and what sits inside it is what we mean by the observable universe. So, how big is it? Here's the answer that feels obvious, and it's a completely reasonable answer, and it's wrong. The universe is 13.8 billion years old. Light travels 1 light year per year, so the furthest anything can be is 13.8 billion light years away, and the whole thing is 27.6 billion light years across. That would be right if space had stayed still while the light was traveling. It didn't. It has been expanding the entire time. Think about what that does. A photon leaves some distant patch of plasma very early on. It sets off towards us. And while it is in flight, for billions of years, the space it has already crossed is stretching out behind it, and the space it has yet to cross is stretching out in front of it, and the region it came from is being carried further away the whole time. The photon still travels at the speed of light, always, in whatever patch of space it happens to occupy. But the distance between the two ends of the journey grows during the journey. So when that light finally lands in a detector on Earth tonight, the matter that emitted it is nowhere near 13.8 billion light years away. It has been carried much, much further out. When you work through the expansion history properly, that matter is now about 46.5 billion light years from us. That's the radius of the observable universe, which makes the diameter roughly 93 billion light years. 93 billion light years across, in a universe that has only existed for 13.8 billion years. Nothing has traveled faster than light to achieve that. Space itself simply has no speed limit, because a speed limit applies to things moving through space, and this is space doing the moving. Now, 93 billion light-years is not a number a human mind can hold, so let's shrink it until it is. Imagine the entire observable universe reduced to the size of a football pitch, 100 meters end to end. At that scale, the Laniakea supercluster, the vast flow structure containing 100,000 galaxies, is about 0.5 millimeter across, roughly the thickness of a fingernail clipping. The local group, our Milky Way and Andromeda, and their 80-odd companions, is under 1/100th of a millimeter. Invisible. You would need a microscope. The Milky Way itself, 100,000 light-years of stars, is 1/10,000th of a millimeter. That's smaller than most bacteria. And the solar system, out to the edge of the Oort cloud, is smaller than a single atom. The distance from the Earth to the Sun, on a football pitch scaled to the whole observable universe, is around the size of an atomic nucleus. Every measurement in this entire story, every transit of Venus, every 11-year voyage, every night Bessel spent at a heliometer, was carried out inside a volume smaller than a nucleus on that pitch, and the pitch is full. As far as any telescope can see, in every direction, there are galaxies. How many is genuinely uncertain, and I want to be honest about that, rather than quote you a confident figure. In 2016, a team led by Christopher Consolis extrapolated from deep Hubble imaging and put it at around 2 trillion. That number circulated widely. Since then, measurements of the total faint background glow of the sky, including some very careful work by the New Horizons spacecraft, out past Pluto, where the inner solar system dust is not in the way, have suggested that estimate was too generous, and that a few 100 billion is closer to the mark. Either way, take the smaller figure. A few 100 billion galaxies, each containing something on the order of 100 billion stars. Point a large telescope at a patch of sky the size of a grain of sand held at arm's length and expose for long enough, and you will find thousands of galaxies in it. Hubble did exactly that in 1995 with the Deep Field, aiming at an area chosen specifically because it appeared empty. There is no empty. Every apparently blank patch of sky is full of galaxies too faint to have been noticed. So that's the observable universe. 93 billion light-years wide, a few 100 billion galaxies, 13.8 billion years old, and every bit of that measured by climbing from a shadow in Alexandria to a well-timed transit, to a pulsing star, to an exploding white dwarf, to a faint hiss in a radio antenna, each rung standing on the one below it. Which leaves the last question, the one you have probably been waiting for. What's outside? And the honest answer is that we don't know, and there is a good chance we can never know. But we are not entirely without evidence. Here's what we can say. The observable universe is not the universe. It's the portion of the universe close enough for light to have reached us in 13.8 billion years. It is a bubble centered on the observer, and the observer is us, purely because of where and when we happen to be standing, which means that bubble is not special in any way. Someone in a galaxy at the very edge of our observable universe has their own bubble, 93 billion light-years across, centered on them. Half of their sky is a region we cannot see, and they, looking back towards us, see us at their own edge. There is no reason to think the universe stops just past the point where our light runs out. Why would it? What mechanism would make the cosmos stop at precisely the radius our own light happens to run out at? That would be an extraordinary coincidence. It would mean the cosmos happened to end precisely where our particular vantage point stops being able to see, which is roughly like assuming the ocean ends at the horizon, because that's as far as you can look. We can go a bit further than that, though, because the geometry gives us a handle. General relativity allows space to be curved on the largest scales, curved one way, like the surface of a sphere, and the universe closes on itself and is finite. Curved the other, or not curved at all, and it can be infinite, and curvature is measurable. Those tiny hot and cold patches in the microwave background have a known physical size, set by the physics of sound waves in the early plasma. So you know how big they really are, and you can see how big they appear. If space were curved in between, the image would be distorted, magnified, or shrunk in a way you could detect. The Planck satellite measured this to very high precision, and within the limits of what we can measure, space is flat. Not approximately flat in a hand-waving sense, flat to within a fraction of a percent, which doesn't prove infinity, because a large enough sphere looks flat from any small patch of it, exactly as the Earth does from a field. But it does put a floor under the answer. If the universe curves at all, it curves so gently that the whole structure has to be vastly larger than the part we can see. Conservative estimates from the curvature limits put the total at somewhere over 250 times the observable universe in radius, and that is a lower bound, not a measurement. 250 times the radius means well over 15 million times the volume, and that is the floor. It might be far larger. It might have no edge at all. There is one more thing about the edge, and it's the part that changes how you think about the whole picture. Because the horizon is not fixed. It's moving. And in one important sense, it is closing in. Remember that the expansion is accelerating. Dark energy is pushing space apart harder and harder as time goes on. Now think about a photon leaving a very distant galaxy tonight, aimed straight at us. It travels at the speed of light through whatever patch of space it occupies, but the space between that galaxy and us is stretching. And if it's stretching fast enough, the photon loses ground. It covers a light year every year, and the gap grows by more than a light year in that same year. That photon never arrives. Not late. Never. Which means there is a second boundary out there, different from the particle horizon. The particle horizon is about the past. It marks how far we can see. This other one is about the future. It marks how far anything can ever reach us from, no matter how long we wait. It's called the cosmic event horizon, and it sits at roughly 16 billion light years. So compare those two numbers for a moment. We can see out to 46.5 billion light years. But anything currently further than about 16 billion light years away is already permanently beyond contact. Light it emits from now on will never get here. We can still see those galaxies, because we're receiving light they sent long ago when they were much closer. But we are watching a recording of something we have already lost. Work out the fraction, and it is sobering. Something like 94% of the galaxies in the observable universe are already outside the event horizon. Unreachable. Not merely too far to visit with any imaginable technology, but causally severed. Nothing that happens there can ever affect anything here again. And galaxies keep crossing that line. One by one, as the expansion accelerates, more of them slip out of contact permanently. So run the film forward, a long way forward, and the sky empties. In about 4.5 billion years, the Milky Way and Andromeda merge. Over the following tens of billions of years, the rest of the local group falls in as well, because gravity holds it together against the expansion. What ends up sitting here is one large elliptical galaxy, and it will be gravitationally bound and stable for an extremely long time. Everything else goes. Virgo recedes. Laniakea recedes. The entire cosmic web stretches away, and its light redshifts further and further until the wavelengths are longer than any instrument could plausibly detect. Somewhere in the region of 100 to 150 billion years from now, an observer here would look out at the sky and see stars, and beyond them, nothing at all. No other galaxies. An island of stars in an apparently infinite void. And here's the part that I find genuinely unsettling in the best possible way. Astronomers on that world, if there are any, would be perfectly intelligent and perfectly rigorous, and they would be able to do excellent science. They would map their galaxy. They would measure their stars. And they would conclude, from all available evidence, that their single galaxy was the entire universe, sitting static and eternal in empty space. They would not be able to discover the expansion, because there would be nothing external to measure a redshift against. They would not find the microwave background, because 13 billion years of further stretching would have pushed it out of reach. They would find no evidence of a beginning. Everything in this story, every rung of the ladder we have climbed tonight, only works because we happen to be alive at a moment when the evidence is still visible. Cepheids in Andromeda, supernovae in distant galaxies, the afterglow of the beginning, still just warm enough to detect. All of it is temporary. The window is open now, and it closes. Two cosmologists, Lawrence Krauss and Robert Scherer, wrote a paper about this in 2007, and the implication they drew is one worth sitting with. We tend to assume that scientific knowledge accumulates, that future observers always know more than we do. In cosmology, that is simply not true. The information is leaking away. There are things we can measure tonight that will be unmeasurable forever afterwards, which turns the whole exercise around. It's not just that we happen to be able to see the universe. It's that we happen to be able to see it now, in a relatively narrow stretch of cosmic time, when the record is still legible. And the record has already been read by an odd and scattered chain of people, most of whom never met and never knew what they were contributing to. A librarian with a stick in Alexandria. A man on Rhodes watching an eclipse cover 4/5 of the sun. A German mathematician who trusted 8 arc minutes of error more than he trusted a circle. A Danish astronomer who realized a moon was not late, the news was. A French astronomer who lost 11 years and a wife to a cloud. A Prussian who chose a boring star because it moved quickly. A deaf woman in a basement at Harvard, paid 30 cents an hour, who found the key to the size of the universe and was told to get back to her assigned catalog. A boxer with a pipe who wrote one word in red ink on a photographic plate. A priest whose physics Einstein called abominable and who turned out to be right. 2 engineers who cleaned pigeon droppings out of an antenna and could not get rid of the hiss. None of them could have finished it alone. Each of them handed something up. That's how you measure something you can never reach. Not in one leap. In rungs. So let's come back down. We went out a long way tonight, and there's no need to leave you out there. Let's walk it back in, slowly, the way you came, and you can stop paying attention at any point along the road. Start at the horizon. 46.5 billion light years out, in every direction. A boundary that isn't a wall and isn't a place, just the distance at which the universe runs out of time to have told us anything. Past it, almost certainly, more of the same, going on for a very long way, possibly without end. Come inward. The cosmic web, filaments of galaxies strung through the dark, meeting at bright knots, separated by voids hundreds of millions of light years wide and almost perfectly empty. Most of the universe by volume is those quiet rooms. The structures are the thin walls between them. Inward again. Laniakea, 520 million light-years of galaxies, all drifting together in one slow current. Then the Virgo cluster, a couple of thousand galaxies bound in a knot 54 million light-years from here, with our own small group falling gently towards it. Inward, the local group, 80 or so galaxies across about 10 million light-years, mostly faint dwarfs, dominated by two large spirals turning slowly towards each other. One of them is Andromeda, 2.5 million light-years away, approaching at 110 kilometers a second, due to arrive in 4.5 billion years. Visible tonight, if your sky is dark enough, as a small pale smudge you could cover with a thumbnail. Inward, the Milky Way, 100,000 light-years of stars arranged in a flattened spiral, a few 100 billion of them, turning once every 230 million years. The last time this part of the galaxy was where it is now, there were no flowers on Earth. We are 26,000 light-years out from the center, in a fairly ordinary stretch of one arm, not central, not special, comfortable, inward, the nearest stars, Proxima Centauri, 4.25 light-years away, a small red dwarf too faint to see without a telescope, 40 trillion kilometers, 70,000 years for our fastest spacecraft. Inward, the solar system, the Oort cloud, a vast sparse shell of ice out at the fringes, Neptune, 5.5 light-hours away, Saturn, Jupiter, the asteroid belt, Mars, and then the Sun, 150 million kilometers from here, 8 minutes and 19 seconds of light, the number that 11 years and a shipwreck and a cloud over Pondicherry went into establishing. Inward, the Moon, 384,000 kilometers, 1.33 light seconds, close enough that 12 people have stood on it, far enough that every other planet in the solar system would fit end to end in the gap, drifting away at the speed your fingernails grow, and there are mirrors sitting in the dust up there, quietly waiting, being pinged by lasers from the ground. Inward, the Earth, 40,075 kilometers around, measured first by a librarian with a stick and a shadow, and the counted footsteps of professional walkers. Inward, the country you're in, the town, the street outside, dark now or nearly, the building, the room, the bed, and you, lying in it, made of atoms that were assembled inside stars that died before the sun existed, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it was manufactured in stellar cores and scattered by supernovae into the cloud that eventually collapsed into this solar system, which means the material you're made of has already been most of the way through this story. It was there for a great deal of it. So the honest answer to the question, the one we set out with, is this. The universe is at least 93 billion light-years across in the part we can see, and vastly larger than that in total, and quite possibly without limit. And it is knowable. That's the surprising bit. Not that it's large. That a species confined to one small planet, unable to physically reach anything beyond its own moon, worked the whole thing out anyway, from the ground, using angles and patience, and a willingness to trust the arithmetic over the intuition. You don't have to remember any of it. Genuinely, none of it. Not the numbers, not the names, not which century the transits happened in. The universe is exactly that size whether or not you can recall the figure in the morning, and it has been that size for a very long time, and it will go on being that size long after everyone who ever measured it is gone. The whole thing carries on perfectly well without being watched, and it's carrying on right now. The space in this room is expanding, very slightly, though gravity and the ordinary bonds between atoms hold everything here together, far too firmly for it to make any difference. Light from Andromeda that left before there were humans is landing on the roof above you. Neutrinos from the core of the sun are passing through the building and through you and out the other side without touching anything, several 100 trillion of them every second, and they will keep doing that all night. Somewhere out at the edge of what we can see, in a galaxy whose light left before the Earth existed, the expansion is quietly carrying something past the boundary, permanently, forever, and it makes no sound, and nobody notices. None of it needs anything from you. So let that settle now. Let the numbers go. Let the names blur. The dates come loose. The distances stop meaning anything in particular. What's left is just this. You're lying in the dark on the surface of a small, round planet, 26,000 light-years out from the center of an ordinary galaxy, on the inside edge of an enormous and mostly empty structure that has been expanding gently for 13.8 billion years. And it's still expanding, slowly, patiently, all around you, in every direction, without any hurry at all. The moon is drifting away by the width of a fingernail each year. The galaxy is turning, and it will take another 230 million years to come back round. The light is still arriving, from everywhere, all the time, carrying pictures of things that happened before anyone was here to see them. There's nothing to do about any of it. So just rest. Let your breathing slow down. Let the weight of the day come off your shoulders and go into the mattress. It's all still out there. It'll all still be out there in the morning, exactly as large, exactly as old, exactly as quiet. Good night.